Okay, we can probably get started. I'll just share whenever.
Yeah.
Okay. Great. So thanks everyone for your patience with this workshop. I had an NIH submission last week. That was a nightmare. And like literally I was dealing with it for 12 straight hours. So it like went right through this. But great. It looks like everyone is here that's typically here. So this is going to be an applied workshop. So we're going to be going through some live coding through a Jupyter notebook. The main goal then being, getting a general idea of how to apply. We're going to be looking at the long short-term memory networks, so LSTMs. We'll be applying it to a very small snippet of the Mimic3 data set. So it's actually publicly available, so I can share the link. And I have the data set inside of the GitHub repo, which I'll show you in a moment. I wrote the final workshop, which was going to be a applied transformer model workshop. It's quite complicated overall. So my question for the folks, because you three are usually amongst the ones that are consistently coming. I've shared the Transformer Jupyter notebook. Would you like to have a partial workshop on it next week? Meaning we're probably not going to get through all of it, and especially because it takes 10 minutes or so to run the transformer on a local device. Or are you okay with the transformer model Jupyter notebook? And then you can, of course, ask me any questions about it. I could schedule a meeting with you or something along those lines. So what works for folks?
Either is fine with me.
Okay. Okay. So I can walk through the notebook with folks that are interested. And just for reference, Randall, I don't have a presentation on that one. It's a live coding, or else I would do that one, regardless, right? But I don't have an actual conceptual lecture written for that one yet. The NSF or the NIH proposal basically blew all of my time out of the water. Okay, well, regardless, today we're going to have a live coding session for LSTM models, and we'll work through that. Yes, of course.
I'm just not quite clear on what the options are. You said you
Sure.
sent to us. Did you send an email to us?
So no, the email isn't out yet. So I was
Oh,
basically, after hearing your responses, I was going to send out the email that has the Jupyter notebook linked. So next week, right, it would be a live coding session like this one. So there would be no slides. Otherwise, I would do that workshop. But with the Jupyter notebook, the two options, one is give the live coding session like what I did with the deep learning one and then with today. The second option is, which for reference, that would be an incomplete one. It's unlikely that I would be able to get through it all in an hour. The second option is you'll have access to the Jupyter notebook and the data and everything, and then I can meet with you to answer any questions about any of the code or to walk through it with you.
what would you prefer?
Probably the second,
Oh,
because
that's fine with me. I
yeah,
don't want to force you as
okay.
I'm the only person that wants to do it. I can do it on my own and ask you questions.
Yeah, I mean, it's mainly I typically don't like giving workshops where I can't complete the material. It's usually challenging for me. Um, and it usually leaves too many open-ended, open-hanging questions. So I can devote that time instead to answering questions in meeting instead. So that way it kind of balances it out. But okay, I appreciate the flexibility. So give me one, I need to set up one last thing in like 30 seconds. Okay, I'll share my screen. find the right one. There it is. Okay, so we're going to be writing through some Python code to the Jupyter Notebook, and it's going to, oh, is there anything in the chat? No. Okay. It's going to cover the long short-term memory networks with the Mimic3 demo data set. So the general idea that we're trying to do is predict ICU stay length based on some lab results that are found within that data set through the LSTM. So the kind of spoiler alert is it doesn't do a great job. So this is because the data set's quite small. It's only 100 observations, which is really tiny for something like this. The full Mimic3 data set would be sufficient. But we're just kind of demoing it. And if I ran the full LSTM on that data set, I would have to run it on like a supercomputer. It would take way too much actual computational space. But this exact methodology could be utilized in, the more complete version. Okay. So for reference, the link with all of, the materials can be found in this GitHub repository. I just pasted it in the chat. I'll have the chat open as well for questions. So I'll glance at every once in a while. So inside of the notebooks folder here, we can find the 3 Jupyter notebooks in total that I'm utilizing. So we have this first one that we have already done a couple weeks ago, or a few weeks ago now, the PyTorch and the XOR data set. The second one is the Mimic data, the Mimic Jupyter notebook. So you can actually click on it and it'll pop up. This is everything that we'll be doing today. And then this third one is that Transformers one that I will send out as well, but this is where it lives. It looks like it was a little pissed off right there. I'll fix that. So the data set that we're going to be using today, you can actually grab because the Mimic3 is able to be utilized without any restrictions. So for reference, this is a groomed version here, this Mimic data. It's still quite large, so it can't just view it. I use this Python script here, this demo subset. So what I did is I had certain qualifiers to give me, we have the ICU stays, the lab events, and then the patients themselves, so we can get information. It's a relatively relatively simplistic subset, just because I had to make it as the least complicated as possible. So to actually go ahead and utilize this data set, I'll give you the raw link. So if you click on the raw file, this is that actual data set. There's no actual identifiable information, so we're in the clear. And let's put this in the chat. Oops, no, it disappeared. So this is that raw link that I'm going to be reading in the data with. Okay. I've already run these functions here. These are installing required packages, so you can see that all of the requirements were basically met, which is awesome. We have the watermark, which is really helpful for, version control and figuring out what versions of things people are using. But we're having to install PyTorch, scikit-learn, pandas, and NumPy for this workshop. Okay, so it's typically best practice to have everything at the top. So basically all of your imports are going to be in the same location. So what we're going to do is have a few different categories. First thing we're going to have, we'll do a little pound sign for annotation, import specific classes from PyTorch. So the specific classes are things like neural network. There's an optimization class we're going to be bringing in, and then things like data loader and tensor data sets. Right. So first we'll import Torch. So that's PyTorch overall, and make sure that this is. Yeah, it looks like it's a Python cell. Yep, it is. Great. We'll then import torch.nn, neural network, as an n. We will also import torch.optim as, so that's the optimization. So optim, these optimization functions are going to allow us to basically go through and make sure that our model is optimized and the different data runs that it's going through. So it'll be able to essentially train itself a little bit more. We're going to say from torch.utils.data import data loader. So the data loader is a way for us to do everything we need to do with our data and prepare it without having any repetitiveness inside of the neural network function. We're also going to have torch data, or tensor data set, so that's going to allow us to convert any NumPy arrays that we're going to have into tensors at some point. Okay, if we run this, let's see if it's PO'd. Nope, it looks great. All right, so the first thing we need to do, because we are, for reference our question, we're looking at the stay, patient ICU stay length based off of the lab results. So in that data set, first thing we need to do is we're going to end up reading it in. I just didn't have, yeah, I forgot to put that there. We do have a few more packages to load. I just wanted to, I guess, skip ahead unintentionally. Okay. So we're also going to import some pre-processing modules from scikit-learn. So we're going to import pre-processing modules. We're going to say from sklearn.preprocessing is your data set in a pandas data frame. It will initially be yes, and then we will convert it to a NumPy array. Yes, pre-processing, import, min, max scalar. Whoops. So that is going to allow us to scale our data sets from 0 to 1. And this is really important for a lot of the numerical data because we actually need to have the same scaling or else it can skew the results a little bit. From sklearn.metrics, we're going to import mean absolute error. This is going to give us essentially the deviation from what we expect in what's called a mean absolute error. I can't remember if I went through that already, but I will. Essentially, the definition is it's going to quantify the average, essentially the multitude of errors in predictions. So it gives you the average absolute difference between predicted and actual values. And there is let's see if I can find I'll paste the Wikipedia that has the formula in here. Okay. So a mean absolute error, we need to import pandas and NumPy. So import pandas as PD, import NumPy as NP. And then we also need to import itertools. So it's going to allow us to do iterations and a little later. Okay, let's see. Yep, that still all looks great. So in this next section, we're going to be doing some data loading and pre-processing. First thing we need to do is convert certain columns to numericals, because basically everything is strings at this point, and we're going to coerce any of those errors to missing values, NaN. We'll convert a date, so stuff like chart time and date of birth, it will go to date time. We'll remove missing values from the length of stay, and then the value number, whatever that column ended up being. We'll then check some data info to see if it's clean, right? So the first step that we need to do is bring in our data. So we're going to say read in data. The mimic underscore data is going to equal pd dot read CSV. And we're actually going to paste that link that I put in the chat, that raw link, because we can just read in the actual data from there. So we will then say mimic data info. I think that was the wrong info. Yep. Yeah, so sometimes with these pandas data frames, when they're being read in, even though I exported it as a pandas data frame and I corrected all of these column types, All of these right here are objects. So there are several of these that we're going to have to change, like I mentioned. So that's just the rationale. So obviously, the length of stay, different things that are numerical values. So if we take a look at head, yeah, we can see that a lot of these are numbers. This is definitely a date, but most of this stuff is numbers. Really only 1, 2 of these should be categories, but I typically only edit the column types of the ones that we need, just because otherwise a little more tedious, and I'm going to be removing those data anyway. So we're going to be converting, so convert columns to the appropriate type. The first thing we want to convert is we're going to focus on this LOS, length of stay, and this is in days. So it's 1.6325 days right here, for instance. I'm going to say mimic data equals, or mimic data bracket. So this is going to be our indexing, and we can see all of these values, length of stay, equals PD2 numeric. And we're going to say mimic data again, and still use that LOS, comma, errors equals coerce. Okay. So what I'm going to have is mimic data.info to take a look every time we do any of these conversions. So let's see what happens. Yep, so that turned into a float value, which is what we wanted. The next one that we need to address is mimic data value number. So it's this value number here. And I'm going to more or less cheat because this isn't a data wrangling lecture, but everything is exactly the same except for it should be value number here. And we're going to do the same. We have 2 more. This first one is chart time. The chart time there. The difference is that we need this to be a 2 date time because that was a date. Same here for the date of birth, DOB. DOB. Okay, so if we take a look, we have an error here because of a syntax error. Equals. Okay, so it looks like all of our changes were in place. There's some other numbers that we have there, but we're not going to be paying attention to those. So we'll end up removing those. I think I end up actually completely removing them. Let's see. Yeah, so let's do that now. We will end up subsetting it because we only want, let's see, length of stay. You know what, let's just do it. We'll convert everything because I think I actually do want to use everything in here. So let's take this same value. We're going to do the subject ID. We'll do the ICU stay ID. We'll do the item ID. And then we need the value as well as value num. This is more, I would say, demonstrative purposes. I would probably get rid of these, but it might as well just see if it fixes anything. Yep, so these all look good now. We only had 2 objects. Okay, great. The next thing we need to do inside of here is remove any missing values. So we need to say remove NA ends. We're going to say the clean data, we're going to call it clean data equals mimic data dot drop NA. In particular, we want to drop from subset equals. So subset equals is going to allow us to designate which missing values we in particular want to remove. So we want from the length of stay and value num. So then that should give us our clean data. Okay. This next step is to group the data by patients and time, because we want to actually group together the patient ID and then the subject ID and then the chart time. So the reason that we're doing this is we are segmenting the data into our sequence, basically. So for each patient, for each unit of time that's utilized. To do this, we're going to say clean data dot sort values. So technically not grouping, but it's more sorting the individual values in the correct order. I'm going to say subject. I'm not going to call that group data. I'm going to say sort data. Subject ID. Excuse me. Oh yeah, we need brackets because it's an index, and comma, chart time. In place, so in place equals, that's going to, let's see what that does, just to double check. Yeah, so it's going to be, let me see. I meant to actually look this up. It will hold sorted data frame. And, okay, so the data frame is going to be intact. That's the issue. That's the concern. So when we run that, we have a key error: chart time. Okay, should be all right. Yeah, because it's saying it's trying to be a copy of a slice from a data set, which is what more or less we want. Okay, so our next goal is to create sequences for our actual LSTM input, right? So why are we doing this? Because it requires a sequential input. So we're going to convert lab results over time into sequences of different length. So we're going to say 10 timestamps. And that's what's going to be fed into the actual LSTM model. We're also going to scale lab values to ensure that the features contribute equally during training. So this typically does help with convergence of the model. Okay, so let's first say, so I'm going to do this in the way that's scalable. So features equals, in this you can say a list, whatever list you want to normalize. So in this case, we're going to be doing value number, but you could say comma, something else, etc. But we'll just do one value. So the next step would be to say scalar, the scalar that we're going to be using is equal to min max scalar. We can then say clean data and bracket features equals scalar dot fit transform. So this means fit and transform whatever's in the parentheses, clean data features. So the reason why I did this method here is you could have whatever that list is. So now instead of listing it here, it's whatever the list of values is up here. In this case, it's one column, but it could be several columns if needed. So, we could add value. We could add, let's just say it's those two. So now when we run through it, it would go through and scale those two. Our next part is actually going through and creating the sequences. So this might take a little, so it's a short little definition. Well, short, still about 10 lines or so. Let's work through each of these steps. So let's create sequences for LSTM input. We're going to say define, create sequences from whatever the data frame is and the sequence length is. So what this is saying is the variables that we can tweak is whatever that data frame object is, and then you define the sequence length, which we're going to define as 10 later. A colon, it's going to go down and have an indent. So the sequences have to first be an open dictionary, meaning that it's blank. The targets also blank. So the sequences are the set of values that are being grouped together by the length. The actual targets are the values that are being put into those sequences, I believe. So for this little blank, that's basically a way, it's a filler for the group in data frame. So whatever is in data frame. So it's kind of like a for whatever is within the group. Group by. Yes, you're correct. It's a list. The dictionary would be the curly brackets. Thanks for the correction. Okay, so we're going to say df.groupBy subject ID. So it's a for loop instead of, so it's already getting complicated. That's okay. We're going to say values is going to equal group features dot values. That's the actual values themselves for each of these groups. In this case, give the values. So this is first part of this for loop is getting those individual values based off of that group or the grouping. So we're going to say if the length of values is greater than or equal to our sequence length, meaning that you are only going to be doing this when the length of values that are being added up. So it goes through an iteration where it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the sequence length, it'll run this next part. Otherwise, it's going to wait until it gets up to 10 again. For I in range length of values minus the sequence length, oops, plus 1. Okay, so this is for each one of the values in this length of the values minus the sequence length plus 1. It's because the sequences are going to start at 0. They need to be 1 through 10 in this case, or maybe 1 through 9, I suppose. 10 values. We're going to say sequences append the values. So basically, we're taking this empty list, we're appending the values that are within I plus or I colon I plus sequence length plus 1. So everything that's in that set of values that we get within the sequence. Targets dot append. So the targets are what we're actually aiming for, the outputs. So targets outputs would be another word for it. So the targets are going to be appending group bracket colon LOS or colon quote LOS dot values. 0, so it's the values in that specific column. So we are putting together the sequences and then the associated targets for that sequence, for the outputs. Okay, so we have our for loop. We then return. So this is what's being given. np.array. It's a NumPy array. So we get the sequences, comma, np array targets. So after this loop is concluded, it will give us our targets. Okay, so that is our function that we're utilizing. To make it actually work, we need to define the sequence length. So we're going to say the sequence length is equal to 10. We're then going to say X comma Y. So the data is going to say create sequences. The X is going to, so it's going to come, the X is going to end up being the sequences and the Y is end up going to be the targets. So we will get clean data inside of it, comma, sequence length. So we're saying the data frame and that length, which is 10. Okay, so we'll prime this. So we're going to say print f quote shape of x, so the features. Oops. Colon x dot shape. And we can just copy this. So y is going to be the target within the model, and it's lowercase y dot shape. Okay, so to see if this works, we can run this and see how angry it gets. Yep, x comma y, create sequences, and cleaned. Oh, there's a cannot construct a data type from an array. Ah, okay. It's, oh yeah, that's the problem. Turn NP array sequences. Okay. It's worked really well for me earlier today when I tried this. Let's see if I can debug. So the thing that was changed is some of these coercions. So I'm going to get rid of the ones that I don't need for sure. It's the only thing that's different. So let's see if this works now. And I'll go through and figure out what the bug is if it's not this. Okay, so it wasn't that. Okay, so let's see. Doesn't like that there's an array element of the sequence, requested arrays and ominous. So the shape dimensions are off. So we have a list of sequences and it isn't liking being converted to an array. So that's interesting that it worked on my device. Oh, and went and did that again. I mean, that looks pretty much identical. Nope, something was different. Very interesting. Okay. So group by the subject ID, values in the group features. Okay, interesting. Really just that the indentation's wrong? No. Ah, here it is. It needs to not have that +1 there. Okay, yeah, sorry about that. It's one of those bugs that whenever you're creating loops, it's hard to diagnose them. Okay, well, that was great. So we need to move on to preparing our data loader to run the model. Oh my goodness, it's one of those days. So we need to create our tensors. So this is going to come from the NumPy arrays that we just had. So this will now work then with creating a tensor data set. So we'll say X tensor equals torch.tensor, X comma D type equals torch dot float 32. So we're going to convert it all to that. We'll keep it at that type. I'm going to say Y tensor equals torch dot tensor, Y comma D type equals torch dot float 32. Okay, so let's run that just to make sure. That worked, great. We'll then create our data set. So the data set that's going to go into the model is a tensor data set, X tensor, comma, Y tensor. The data loader that we're going to utilize is equal to data loader, data set, comma, the batch size. So this is the number of batches we're going to be creating within our data set. So breaking it up so it's not all running at once. We're going to say batch size is 32 and we're going to shuffle it. So shuffle equals true. So when we run that, yep, looks good. Okay, so the next step is to define our LSTM model. So we need to define an LSTM with hidden layers that's going to output a single value. So it's going to be our ICU length stay or stay length, all right? So it uses internal memory to capture these long-term dependencies, which is why it can really eat your working memory, but we'll give it a go. This model shouldn't be complicated enough to freeze up, but double check. Let's wait and see. So the class we're going to create is LSTM model from neural network dot module. We're going to go down and say define, so initialize, so whatever is coming out of here. We're going to say the self, so the model itself, the input size, the hidden size. The input size is how big our input layer is. Our hidden size is the size of our hidden layers. The hidden layer, the number of layers that we're going to be utilizing, and the output size. So I'll fill these in later, but the input size is all of the features. The hidden size, we're going to say 64, so 64 deep, I suppose. 2 layers that we're going to be utilizing. So 2 should be, I'm thinking it's going to be that there are 2 layers. There's a hidden layer and then the output layer, but it could be 2 hidden layers. And then the output size, which is going to be 1. Okay, so we'll say colon, the superclass that we saw last time, which basically is calling this model, LSTM model, comma, self dot init. So initialize the model, self dot LSTM, so the function itself that is being called within this LSTM model. It doesn't need that. We're going to say self.lstm equals nn.lstm input size, comma, hidden size, comma, number of layers, comma, batch first equals true, meaning that we want the batches to exist that we've created. Okay, we're going to say self.fc, so that's the that is the forward. Man, it is one of those days. I ran out of coffee today, so it's been a blast. It's like it's a feed forward network, so it's going to be moving forward. So we're going to say nn.linear hidden size, comma, output size. Okay, the next step we need to do is define the forward. So the action of how it's moving through the network. We're going to use self and x, so x is the input. H sub 0, so that initial hidden layer, the initial, is going to be torch dot zeros. And then it's basically a bunch of zeros. The number of layers, comma, x size, so the size of the input layer of that column, so the first column, so 0 in this case, or whatever is the most recent one it's going to be going through. So hidden size as well. And we're going to say to device, because it needs to go to our working memory. So number of layers is defined, so don't worry, it'll get there. T0. So for that, we're going to say torch dot zeros, and we're going to actually do the exact same. So we have the hidden components, and then the inputs. The C0 is the state, so that's the current state. The out, whatever's coming out, is going to be this kind of blank everything that's within self dot LSTM x comma H0, so the hidden, so the outputs that are coming from the hidden layer, and then the state. So the hidden layer is going to produce outputs at the sequence, and then the state's going to move from one to the next. So C0 is where it's initiated, and then H0 is where the initial outputs are, which are, none, basically. We'll then say out equals self dot fc, so that forward feeding model. We're going to produce an output of bracket everything that's produced, essentially, comma, -1, comma, colon. So this will basically produce, so -1 is like an infinity, it's a whatever size the variable is, and it's the columns and the rows. Return out. Okay, so we have our model classified. We need to now define the hyperparameters. So whatever we need to actually have that's going to be adjusted. All these things are not defined, that it's getting upset with me about. We're going to say the input, size is equal to the length of the features. So all of the features. The hidden size is 64. So 64 nodes is going to go from the number of features to 64 back down to 1, eventually, 1 output for each of these individual components, each sequence step. So the number of layers is equal to the output size is equal to 1. Okay, and just to double check. Yeah, so there's a step I forgot up here that I should have made clear because device was also not produced. So under here, I'm going to add some code that checks our device. So device equals torch.device. We're going to say run CUDA if torch.CUDA is available, else CPU. And then we're going to print f quotes using device colon device. So when we run this, it's going to say it's running the CPU. Okay. So that's good. We have that. We have our hidden layer, the number of layers, our output size. Now we need to initialize the model. The loss function. So what is going to determine, what should essentially be removed and how it needs to train itself again, and the optimizer. So the optimizer is going to be based off of mean square error, the loss of that. So that's going to allow the next layers the next time that we go through epochs, it's going to readjust all of the weights and parameters that we are not actually interacting with. So we're going to say the model is equal to LSTM model input size, comma, hidden size, comma, number of layers, comma, output size. And it's going to go to device. The criterion we're going to be using is equal to no network dot mean square error loss. So that's the loss function. The optimizer is going to be equal to optim dot atom by the model parameters, comma, our learning rate. We're going to keep our learning rate at 0.001. So it's kind of low, which is okay. Let's see what happens. It's running through it. It looks like it's initialized well. Okay, so our last thing, we have a couple things. We'll probably have time for it, which is great. We need to create a training loop. So the more epochs that you have, potentially the better, but there's usually a trade-off eventually. In this case, we don't want to take too long. So we're going to say the number of epochs equals 20. So it's going to go through the data 20 times. We're going to say for epoch in range the number of epochs model.train epoch loss equals 0 for batch x comma batch, because remember we have batches within these epochs as well, in our data loader colon. We're going to say batch x comma batch y is equal to batch x dot to device comma batch y dot to device. So it's whatever is within our device for those batches. So the forward pass, that FP, of what's going to be moving through the model. The outputs are going to be equal to model batch x. The loss is going to be equal to criterion outputs dot squeeze batch y. So squeeze is a linear algebra function that'll basically allow the difference, if there's a different size, it should allow it to work even if it's different. But I think it's just needed for best practices, but we shouldn't need it in ours. I say backward, pass, and optimization. So the backward passing and optimization steps are where the model learns from how well it performed and retunes itself. So the optimizer, we're going to use zero gradient. So the zero grad, that's the optimization algorithm we're going to be utilizing. The loss is our from backward. Oops, we don't want that. We want lowercase. The optimizer is done at each step. So we'll then say epoch loss. So the epoch loss starts at 0 because there isn't any loss. The loss is going to show us at each epoch what our value ends up being. So at plus equals, so plus whatever was an epoch loss, and then it'll equal loss dot item. Lastly, we're going to print f epoch plus 1 divided by the number or over the number of epochs. So it'll give us a progress report essentially. Going to then give us loss as the epoch loss over length data loader colon dot FF or 4F. So that's going to give us 4 degrees of freedom. So not length, it's length. Okay. This will probably, have a bug. Batch X. Yeah, okay. It looks like it's running. It's going to take a second to run through this. So let's get to the next step while it's doing that. Yep, it's about what I was expecting. So let's now do evaluation. So we need to determine how well our model performs. We'll say model.eval predictions equals this empty list. Oops. The predictions are going to come from the ICU stay in our data set. We're going to look at the actuals equals an empty list. So the actuals is what's truth. The predictions are from the model. Actuals are the truth. So with torch dot no grad colon, we'll go down for batch X comma batch Y in the data loader. Batch, we're going to just copy this from above because it's exactly the same. Batch X, Y to device. It looks like it's performing a little better over time. But, ideally we would be having a different set of learning and then more epochs. It just takes too long to even do 20. I'd probably even split the data up more. Okay, so then we say outputs equals model batch X predictions dot append outputs dot CPU. So from our CPU to list actuals dot append batch Y dot CPU. So the reason why the outputs are going into batch X is because the model is producing them inside of batch X. We then compare them with batch Y, which is the truth. So to the list, I need to flatten the lists before conversion to NP NumPy arrays. The predictions are equal to list, iter, tools, chain, from, iterable, predictions. The actuals are equal to list, iter, tools, dot chain, from, iterable, actuals. We then convert to NP array, predictions equals numpy array, predictions, actuals equals NP array, actuals. Looks like it's done and it did iffy. I mean, it's better than the initial one at least, but it just can't really perform as well as it needs to without a more complex data set. Last thing we need to do is in here is calculate the mean absolute error. So MAE equals mean absolute, not median, and mean. When we're looking at the actuals, ACTUALS, by the predictions. We then print the MAE as MAE colon dot 2 degrees of freedom. .52 days off. So it's not great. There's a lot of reasons behind this, but this is the main methodology that you would go through this. So there's some takeaways. So this is actually worse than the one that I performed separately. So it's not really ideal. We would need to make sure that we're doing normalization for all of them if we didn't already. We need to handle missing values in other columns, perhaps, do some feature engineering. We definitely need a larger data set. We can increase complexity. We didn't do that. It's a pretty simple model. We can make it bidirectional, meaning it learns from past and future sequences. There's an attention mechanism that starts going towards the transformers. Otherwise, tuning, hyperparameters, different training strategies, there's ensemble approaches, and so on and so forth. I am right at time. I'm glad we got it over with. I apologize for that bug that happened earlier. And thanks again for that correction on dictionary versus lists. But I can drop into a breakout room briefly, but I do have somewhere to drive off to shortly after. But appreciate it, everyone.